Well, hello there. Today we're going to talk about FETs, Field Effect Transistors. We've been talking about BJTs, bipolar junction transistors, up to this point. And this is a different type of transistor, a field effect transistor. Why is there two different kinds of transistors? FETs are most often used for switching applications. In other words, on or off. Okay, in fact, all integrated circuits are made with FETs, field effect transistors, a bunch of them. I mean, there could be a billion field effect transistors in a common microprocessor these days, or FPGA. So that's primarily what they're used for. There is linear applications, however, for field effect transistors, and we'll look at some ways of doing that. The other main difference between BJTs and FETs is, you remember, BJTs, bipolar junction transistors, have a transfer function, which is the output current divided by the input current. That's called beta, right? So you have collector current divided by base current. That's a BJT transfer function. It's beta. For a field effect transistor, it's different. The output current, which we'll see is called the drain current or the source current, is controlled by a voltage on the input at what's called the gate. Okay, so it's a different transfer function. As a matter of fact, it's called transconductance. It's output current divided by input voltage. And so that's the main difference between FETs and BJTs. Of FETs, there's two main categories of FETs. One is a N channel or a J FET, which can be either N channel or P channel, which we'll see, which is sort of like NPN versus PNP for the BJT world. And then, so that's the J FETs, but then there's also MOSFETs. And MOSFETs are used mostly for higher power applications. They can be control hundreds of amps. And we'll get into that in a minute. So the opening slide here is this person back in 1930, Julius Lilienthal, who made did a patent for the FET. They couldn't make them because they didn't have the materials until the 50s. So they started actually making FETs in the 50s. That's when vacuum tubes are still around. As a matter of fact, a FET, I don't know if you all know what vacuum tubes are, but they're still used today in high power amplifiers, guitar amplifiers, things like that, high power transmitters. But the FET is most closely resembles a function of a vacuum tube, because a vacuum tube also has a transfer function, which is a current controlled by a voltage, okay? Unlike a BJT, which is a current controlled by a current. Okay, so here's the JFET, okay, junction field effect transistor. That's the first kind we're starting with here. And it's a normally on device. So if you don't know, there's three terminals here. Drain, that's what the D is. There's a gate, and that's the source. So these things going up here are actually holes. I believe this is a electron flow model instead of conventional current model. But be that as it may, it's still a three-terminal device, just like your BJTs. The difference is that there's a couple differences. One is they're named differently. This is D for drain, S for source, and G for gate, as opposed to collector, emitter, and base. Okay. The other difference here is that when the gate is at 0 volts, see it's grounded here, we get conduction flow. In order to stop current flow, in order to stop current flow, you have to make the gate, in case of an N-channel device, negative. You make a gate negative with respect to the source. We'll see that. P-channel device, currents just flow the opposite way. So this is a P, these are P's, and the N's are right here. So when we apply a negative voltage to the gate with respect to the source, so VGS, if you will, okay, current shuts off, all right? And it's kind of a nice graphic here. It kind of pinches off the current flow, and the current decreases. So just like bipolar transistors, we have N channel, we have P channel. This is an N channel. The arrow points in. P channel, this arrow here at the gate would be pointing the other direction, and all the polarities would be different. In other words, this VDD would be flipped 180 degrees, and so would VGG. All right. Yeah, for N channel, we always have a negative voltage here on the gate. 0 to negative. We'll see some graphs in a minute. So here's a transfer curve, characteristic curve, showing the VDS, drain source voltage. It's similar to the VCE of a BJT, right? You know, if we go back here, so drain source. So this would be kind of like the collector emitter. Well, it's now VDS this way. And then here's ID. This is the drain current. So this would be like your IC for a BJT. Very similar. The difference you can see here is that these curves, if we do a family of curves, this shows just one VGS as 0 volts. Okay, so with 0 volts, we have current flowing. As long as you have some voltage on VDS or current, you can actually conduct current between the drain and the source. This area here we'll see is kind of a linear curve, and it actually represents a resistor. It's an ohmic. It's called the ohmic region. All right. Right here, let's see, I think they explain this here. A and B is the ohmic region. Yeah, so this is sort of a current voltage related by Ohm's law. We get into this region, it's a constant current area. In other words, IDSS in this case, is constant. Even though you're increasing VDS, it's still the same current. And then when you get past over here, this is breakdown. That'll cause damage to the FET. If you get too high of VDS, you'll eventually break it down. Here's a family of curves, family of characteristic curves, very similar to the family of curves for BJT, except each curve is drawn with a different gate source voltage. Instead of a base current, the gate source voltage changes. And you notice that as the gate source voltage decreases, or becomes more negative, I should say, the current goes down. So we can draw a line here, similar load line, okay, and walk up and down that load line, okay, in a linear, somewhat linear fashion, and actually make an amplifier, a linear amplifier out of a FET, just like we did with the BJTs. Okay. VP stands for the pinch-off voltage. It's 5 volts here, or VDS. That's about right where the constant current operation starts happening. We can plot VGS to ID, okay, the gate source voltage, to the drain current. It's a nice gradual sloping curve here. And fortunately, some very straightforward equations that describe it. Here's one right here. This is the main one you want to be using. And like I said during the last presentation, you want to make some formula sheets for the midterm, okay, and use them now to do your homeworks and do the examples in the textbook to prepare for the midterm in a couple of weeks, or next. It's on November 4th. Okay, so you'll thank yourself for writing these down on a 8.5 by 11 sheet of paper and using all of those formulas to do your homework, because then you can very quickly get to them when you're doing the midterm. You'll need these to do the midterm. But here's the equation that represents this curve, or this is the curve that represents the equation, depending on how you look at it. Notice that the current decreases, the drain current decreases as VGS increases in magnitude, negative magnitude. And we can do a couple of little substitutions. At half IDSS, that's the maximum drain current, IDSS. Half of that, you get a third VGS off. VGS off is where no current flows in the drain. And at a fourth, you get a half VGS off. So that's very convenient. Little rules of thumb there. You might want to write that down on your equation sheet, these two relationships. Because if on the midterm you're given half of IDSF, you immediately know that VGS occurs. This occurs when VGS equals 0.3 times VGS off, and so on. Here's an example, 2458 FET, IDSS of 6 milliamps, VGS off of minus 3.5 volts. So this is minus 3.5 volts down here. This is 6 milliamps. The point for the case for the ID is 3 milliamps. Well, that's half of 6, right? And so based on that last slide, half is 0.3 VGS off based on that last slide that we did. So it's 1.05 volts minus 1.05 volts. It's going to be where that occurs. So bouncing balls here, okay? So the transconductance is delta ID versus delta VGS. So we do a little triangulation here. And GM, that's the transconductance. It's the reciprocal of resistance, right? So the units are not in ohms. The units are in 1 over ohms, or in other words, Siemens, we call it. All right. And formula is for calculating GM. You know GM 0. Okay, and this is a specification that you can get out of the data sheet for the FET. And VGS off is, you can get that on the data sheet also. And you can also calculate it based on VGS off. These are more formulas you should put on your formula sheet. Use them to do the homeworks. And the slope changes at every curve, so it's not linear. It's kind of a slopey kind of curve. All right, so you have to take a couple of points and delta ID here for this example, delta VGS, and you end up with 3.33 ms, millisiemens. Okay. Input resistance of a JFET, really high. That's one of the best things about them. They draw nanoamps at best, picoamps. So it's VGS over IGSS. IGSS is nothing. Okay, it's just very small. It's nanoamps, so the input resistance is huge. So one thing it does change is with temperature, the input resistance does change. The IGSS changes. IGSS is 1 nanoamp at 25 C and 0.2 microamps at 100 C. Still pretty small, okay, but they do a couple of calculations here. VGS is 20 volts over 1 nanoamp. We get 20 gigaohms, pretty high, huh? And 100 degrees C, you get 100 megaohms, still pretty high. Okay, so FETs are used a lot for situations where you do not want to load your source. Okay, so they're used for very low power applications, JFETs in particular. Now, how do you bias a JFET? Well, in order to get things going, right, VG has to be 0 volts or less. Okay, 0 volts or negative, so with respect to the source. So VGS, if you put a positive voltage on the source, your VGS is going to be negative, okay? Even though VG is at 0 volts, VGS is going to be negative because you got a positive voltage here with current flowing. So it's called self-bias. Okay, RS develops a necessary reverse bias that forces the gate to be less than the source. Or another way of saying it, the source to be greater than the gate. And I throw some values in here. What's VGS? 3 milliamps coming down here. ID is 3 milliamps. Well, the only place for the current to go is through the source. So that 3 milliamps passes through the source resistor. So 3 milliamps times 330 is 0.99 volts right at the source. So 0 minus 0.99 is minus 0.99 volts. That's the GGS, VGS. That's self-bias. And you can use the transfer curve to determine a value of RS. So if you want to put the Q point there, your ID is 4 milliamps. VGS is minus 0.125 volts, just eyeballing it. So VGS over ID, 1.25 divided by 3 milliamps. Your resistor ends up being 375 ohms. That's for the source resistor. That's for, let's see, this guy right here, that one. Yeah, 375 ohms. Now you can also do voltage divider bias. We're used to this for the BJTs, right? The problem with self-bias is that, go back here, with these FETs, the VGS might, and ID and IDSS and all these, the input current and things like that, they might vary from FET to FET, okay, slightly, depending on what day the FET's made on and what substrate it's made out of and so on. So putting a voltage divider here, it stiffens it up a little bit and will keep VG much more stable. Still keeps it positive. You can still make it so the VS is positive with respect to the gate, but this stiffens up the gate voltage. Notice that we have so little current going into the gate that we completely don't have to worry about taking into account this source resistor at all, like we did with the BJT where we had an emitter resistor. We had to reflect that into the this circuit in order to determine input impedance, input resistance, and so on. Don't have to do that because there's no current coming in here. It's basically, this is almost disconnected from a current standpoint on the gate, right? Yeah, so VS must still be larger than VG in order to get current going here. And like I said, the voltage divider bias helps stabilize the bias for variations between FETs, transistors. Okay, so here's some graphical analysis of voltage divider bias. So we determine what the voltage is right here at the gate. You can just do simple voltage divider calculation here, which would be 1 megohm divided by 4.3 megohms times 12 volts. If you do that calculation, you end up with 2.79 volts. So 2.79 volts here, and divide that by RS, you get 2.79. You can draw a line here, 2.79 volts, 2.79 milliamps. Draw a line through that, you end up with a Q point right there, which is 3.3 milliamps and 0.7 volts. Now, we can even improve on our biasing if we add a constant current source. Now, this is a constant current source down here, this Q2, okay? And you adjust the offset with this resistor here, the series resistor. And you can adjust for V out to be 0 volts, which is really nice, okay? So if you do apply an AC waveform here to Q1, you can produce amplified V out here amplified version of it at V out, which is zero biased. So Q2 is a constant current source. Okay, here's the ohmic region. Now, FETs can be used as voltage-controlled resistors, okay? And we show this right here. This is the ohmic region to the left here. And as you climb up and down the curves here, VG, you decrease VG, increase the magnitude negatively, you increase the resistance between the drain and the source. And so therefore the current goes down, the drain current decreases. Very common use of a FET is for a voltage control resistor. And we'll see an example of a voltage controlled amplifier here in a moment. Right here, yeah. Okay, so this is a voltage controlled amplifier. This is a BJT. This is our standard common emitter amplifier, right? Which we looked at a couple weeks ago. VL's taken at the collector, okay? But the gain of this circuit is adjusted. You can adjust RE to adjust the gain of this. And what we do is we put this FET in parallel with it to change its resistance. Okay, so this Q2 actually will change resistance between its drain and source, which is in parallel with RE. It'll change its resistance in response to the gate voltage. So you have a voltage controlling a gain. So it's a VCA, voltage controlled amplifier. What are these used for? All sorts of things, automatic gain controls in radios and audio circuits. They're also used in radios for amplitude modulation. Lots of applications for a voltage controlled amplifier. Okay, so that's JFETs. Let's move on to MOSFETs, metal oxide semiconductors. It's the same idea, okay? In other words, it has a gate, a drain, and a source. And the gate current is minuscule still, all right? But they're used normally for more high power applications, okay? Amps to hundreds of amps, although there's much smaller ones too. And there's two main types. One is an eMOSFET, enhanced mode, and one is depletion mode. They're both used for different reasons, and we'll get into that. So enhanced mode has no channel until it is induced by a voltage applied to the gate. Okay, and for an enhanced mode N channel type, you actually apply a positive voltage to it. So it's different than the JFETs. You apply a positive voltage to the gate of a MOSFET, and that causes current to flow. Depletion mode is the opposite, okay? Controlled by the gate voltage for the N channel type, a negative voltage is applied, just like for the JFETs. For operating in enhanced mode, you apply positive voltage. Now that seems confusing, right? Well, it turns out that a DMOSFET can operate either in D mode or E mode, depletion mode or enhanced mode. In other words, another way of saying it is that your gate voltage can either be positive or negative. Okay, and depending on how positive or negative it is will determine the current flow. So it crosses the vertical axis on these graphs that we'll be seeing pretty soon. So here's the symbols. We'll look at those in a minute. Here's the symbols for the eMOSFETs, N channel and P channel. Little lines here with arrows in the middle. And look at that. The DMOSFETs have the same exact symbols. A little scary. You have to communicate a little bit when you're doing schematics on these, and make sure you put the part number next to the schematic symbol or some sort of note to say what it is. So let's take a look at the eMOSFET, enhanced mode MOSFET. It's similar to the JFET, only everything's to the right, right? Because we have a positive gate voltage. Unlike the JFET, it's a negative gate voltage. Okay, so VGS is positive, and the greater the gate source voltage, the higher the current. And so it's a positive transfer function. And here's equation for it. Okay, K is a constant, and that is out of the data sheet. VGS-TH, it's the lowest point of current. That is also in the data sheet. Now, DMOSFET, on the other hand, can operate on either side of the axis when you're talking about VGS. So you can go negative with VGS, or you can go positive, but it's still a positive transfer function, meaning that if you increase VGS towards the positive direction, you get a higher drain current. So this over here on the right is called enhancement mode. This over here on the left is called depletion mode. Still a DMOSFET. So you look at this curve, you know you're a DMOSFET. This is a DMOSFET curve. Now the cool thing about this is you can, as we'll see I think in a minute, you can apply an AC waveform to the gate on a DMOSFET and control drain current. That AC waveform is going to go back and forth across here to positive to the negative, positive to negative, right? And you're going to control the drain current. And that's how FET amplifiers often work. Here's another equation. This is very similar, exactly as same as one of the earlier ones we had. Here's some biasing methods. eMOSFETs bias using bias methods like BJT. So here's voltage divider bias, and this is sort of like a collector bias, but it's drain feedback bias. Very similar. Again, there's no current hardly at all going into the gate here, so the equations are much simpler for these. And with DMOSFET, you got to do zero bias, right? Because you're swinging back and forth across that zero voltage on the gate. Here's what I was talking about earlier, this AC input. It's AC coupled, so this maintains the gate at 0 volts. And as you swing this back and forth across the axis, you get a varying current through ID. And I think we have a couple little terms here. JFET, it's a junction field effect transistor. What's the other type? MOSFET, right? So JFET and a MOSFET. And each one of those have two different types in them, P-type and N-types. In depletion mode, in MOSFETs there's even more. There's depletion mode and enhanced mode. So the drain is one of the three terminals. So it's analogous to the collector, the source is analogous to the emitter, and the gate is analogous, I should say. Analogous, what's that? Analogous to the base of the BJT. Okay? All right, so good luck everybody, and that's it for this week about that. If you have any questions, please put them in the discussion area.